Hi all, I'm first year graduate student and my name is Divyani Srivastav and my project is Asteroid Prediction. So asteroids are small rocky bodies that orbit around the sun. Most of them are found between Mars and Jupiter. Their size may vary from hundreds of kilometers or to few meters. Asteroids which are found near Earth are called near-Earth asteroids and can be a potential danger to Earth. They are of scientific interest because they provide insight into formation and evolution of the solar system. They also contain valuable resources such as metals and water that could be used for the future missions. The goal of the project is to predict the size and the hazardous potential of asteroid since it is crucial for various other reasons and we would be using various ML models to understand. Here are the various milestones or the phases of the project. First, we did data collection and EDA, then we did clustering, then ARM, and then we deployed classification models such as decision tree, naive Bayes, SVM, and then we did diameter prediction using neural nets. We also did diameter prediction using multilinear regression. Then we used classification. Then we did classification for using neural nets, and of course, guys, the limit. So for the data collection, we used NASA API, but due to some constraints and the lack of features, we reverted back using Kaggle data. So as you can see here, there were a graph between diameter and the relative motion. So most of these asteroids, they belong to MBA and their diameter, they vary from 400 to 0 kilometer. Here, so MBA stands for main belt asteroids, and these are the asteroids which are found between Mars and Jupiter. Uh, the other features are aphelion. Aphelion is the farthest point from the sun, whereas perihelion is the nearest point to the sun. Eccentricity is one of another key determining factor. If it is highly eccentric, it might bring the asteroid closer to sun and it might experience heating and change of size, shape, and composition. And if it is very far, there might be some gravitational perturbations. So it shouldn't be much high or it shouldn't be much low. Of course, one of our target variable is diameter as we are doing diameter prediction. And one may think higher the diameter, the greater the level of hazardity or they are dangerous to Earth, but that is not the case. The asteroid is considered potentially hazardous only if it is a near-Earth object, and generally largest asteroids are less common among near-Earth objects because they have greater gravitational attraction to the sun, which causes them to be more stable in their orbit farther from Earth. Here is another visualization of the mean motion. So I did not share all the EDA since there are almost 31 features, but these were the key features which may determine our target variable or which may affect our target variable. Here is one correlation matrix, and these are the various features or these are the various findings from the correlation plot. So clustering. For clustering, we took unlabeled data, and this is how our old data or the original data was. And then we scale the data, and then we used Euclidean distance, and then we plot the clusters. The clusters are very overlapping. We used silhouette method and elbow method to determine the optimal number of clusters, which in both the cases were 4. This is how the hierarchical clusterings look like. It is very evident that it is highly overlapping. ARM, association rule mining. So for association rule mining, we took all the categorical variables and then we converted them to a transactions data set. So for the particular support, confidence, and minimum length, this is how the rules look like when sorted by support. The bigger the points are, the better the rule is, or the most used rule is. This is how they were sorted by lift and confidence. Decision trees. So this is how we did the data prep, and this is how it looks after scaling. And then we use one-hot encoding to convert the label data into numerical. And as you can see, without any pruning, the visualization shows that the tree is overfitted and the accuracy was 99% again, which tells us that the tree was overfitted. After the pruning the depth to 5, the accuracy was again 99%. Again, pruning the leaves, the accuracy was again 99%. So of course, decision tree is not for our data. Then we used NAB bias and we found that the accuracy was 98.6%. Support vector machine. So in support vector machine, this is the results for the linear kernel, and we varied the various cost values, and we had accuracy of about 94.8%, which is more realistic than the decision tree results. These are various visualization of the various features. For RBF kernel, we varied various gamma values, and these are all the accuracies which we found. For polynomial kernel, we varied different degrees and various cost values, and here are the various accuracies. So one thing is that for all the classification models, the data prep remains same, and hence I didn't repeat it again and again. The second part is, of course, the diameter prediction using a multilinear regression. So this is how the initial data looks like. We cleaned it, we removed all the outliers, and here we are using stratification. But prior to stratification, we use binning, and we cut or divided our target variable into various bins. There were 5 bins, as you can see from the graph. And according to that dummy variable, which was a diameter group, we did stratification and we divided our diameter. So these are the results. The R-square value was 65%, which is decent, but not that great. That means the model didn't fit that well to our data. The residual plot versus fitted values, we can see that it is around the line, but not quite around the line. So the next part is diameter prediction using neural nets. This is how a general introduction of neural nets. As you can see, it has an input and output layer, and then there is 2 hidden layers. And in 2 hidden layers, we have activation function. In our case, it is ReLU and linear activation function. So the ReLU provides that boost to the gradient, which it usually loses during the training. And that's how it increases the performance of the neural nets. This was the data preparation. So before our original data was like this, and then we scaled our data. It is similar to what we did for MLR. Then, of course, we did the partitioning of the data. The R-square value was better than the MLR. Here it was 70%. This is a schematic diagram which shows our model. So in the hidden layer, this this is the representation as a model summary. Then we did the classification of asteroid using neural nets. And of course, we had the similar data, and we did this is after scaling and one-hot encoding. And here, instead of using linear activation function to our output, we use softmax. So this is how our model looks. It's essentially the same. Only thing is that output layer, instead of having a linear model, has a softmax function. Conclusion. So, of course, physics is complex, and hence it is possible that the results which it yields is not accurate or maybe displaceable, and hence the problem needs to be approached recursively. In clustering, especially, since the data was highly correlated, all the clusters overlapped. In ARM, we were able to identify rules which can help us associate various features of importance. In classification, DT or decision tree was overfitted, and for that we should use various other models such as random forest or XGBM or cat boost or ada boost. And naive bias and SVM, they perform much better. Using neural network, of course, we got better results in compared to ML. So I hope you all like my presentation and project. Of course, I am learning and I'm looking forward to learn more in my journey. And that's it for today. Thank you so much.